Okay, so
Yes.
maybe we should start. It's not a bad idea. That's what I tell you, I'm the only one here who doesn't get to eat. Okay, it's feeling incredibly guilty. But just feel guilty, I'm good, I'm really good. No, it's like, it will only do me good. Okay, so what did we do? Last time we discussed anatomy. And the rationale for wasting your time on boring anatomical details was to convince you that if you want to do functional anatomy, which is what one does when one does neurolinguistics, or at least part of what one does when one does neurolinguistics, then you need to decide what anatomy is. And for that, the bare minimum would be to parse the relevant pieces of neural tissue into their component parts. That's really the bare minimum. And what I did was very sketchily, I tried to convince you that the intuitive methods of just like calling things by name are not sufficient, and you need to set up borders between different brain regions. And that, at least for now, the best way to do it, with many misgivings and many problems and many disadvantages and many doubts, is by looking at this thing that's called cytoarchitecture, namely by determining regional borders according to the microanatomy as seen by the laminar structure of cortex in specific regions, which is studied very laboriously by very diligent, serious, and sophisticated computational anatomists, mostly in Munich, in Germany, which is my favorite place. And the end result, with again tons of assumptions that I will be more than happy to lay out to whoever wants to hear. Yesterday I forced it a little bit on Martin, but if you'd like, I'll be happy to talk to anyone about the advantages and disadvantages. But this is basically the best game in town if you want to stick to the anatomy. So we've done something that's called cytoarchitecture, cytotonics, and now it's time to move to functions. I mean, you're linguists, you might be interested in functions. And we're moving to functions, and the functions chapter is going to have two pieces. Piece one is to talk a little bit about monotonicity. I'm not going to start with monotonicity as a concept or something, but I will end up with something like that. And I want to describe to you the path towards the end, because the conclusion would end up being a kind of simple linguistic conclusion plus some anatomy, but it's going to be a fairly simple linguistic conclusion. So I want to get there in the end and show you the path, because the path is an experimental path. And what I will do is I will go, in each case, I will discuss it in several ways. First of all, the dependent variables that we're going to be discussing are going to be error rates. They're going to be basically continuous variables. So error rates, which go from 0 to 100 or something, or to 1, from 0 to 1. They're going to be reaction times, and they're also going to be brain segment intensities or indices of brain activity that are specifically, the hope is that they're specifically localizable to a certain piece of brain tissue, which might be informative to us. And we want this kind of information. So this is the dependent variables. The order of things is going to be, first we're going to look in each case. This is what I've been doing in my lab for a long time. We're first going to go the cheap way, and we're going to look at just behavior. And then we're going to move to fancy stuff with big magnets and machines and a lot of grant money and all this kind of stuff. And since Enrico's is here, and he just got up, I will tell you an anecdote from Italy.
Oh, I thought you wanted money.
No. So there, you may know that Italy has been very rich in neuropsychological activities. There's a lot of neuropsychology in Italy. Okay, you learned something new. Mostly in Milan. And I once heard from some old timer how it all started. In the 1950s, the late 50s, they had a visitor from Iowa, some neuropsychologist named Arthur Benton. I'm sure you never heard about him. He developed neuropsychological tests, and he was there on sabbatical. And they came to him and they said, we want to do research, but we don't really have money. What do we do? And he told them, do neuropsychology, it's cheap. And he was right. He really was right. And I think it's a good strategy. You know, your research is incredibly cheap. Okay. But if you go one step away from you go to like behavioral experiments and things of that kind. And I think it's always the safe way to start off with cheaper experiments. It so turns out the standard behavioral experiments that measure error rates, and especially that measure reaction times, if you do it right, they're relatively less noisy than elsewhere. Less variability, less intrusion, you know, fewer, sometimes you need fewer controls. It's the sound way to start off. And I never have subjected people's brains to any test before I subjected any brain test before I tested. I made sure that this experiment works outside of the magnet, namely just in some basic experiments. So we're going to start off with cheaper, less noisy behaviors and continue to more expensive rates. And the question is, what are the micro modules which are functional? And we're going to start with monotonicity. It's not really, it's just a name, because the question is, what is monotonicity? Why should it live in a brain? And I prefer to postpone these questions for later. It's not as if I'm glossing over them, but just I want to tell you a story. So the story starts actually in the late 1960s, where people started being interested in psycholinguistics, at least people started being interested in negation. And the first ones to do anything of that kind the first one was Herbert Clark, a very distinguished psycholinguist at Stanford, who I think is still active actually. I think he should be in his 80s, but as far as I have seen, I think he may have been active over the past few years. And he did a whole bunch of very interesting experiments, and here's one. So the question is, when we look at antonyms like above and below, and we look at sentences with and without an explicit and overt negation, what do we get in terms of processing costs? So the experiment was quite simple. You get these 4 types of sentences. You get 2 types of images, true and false. You get one of them one at a time, and you get to indicate, is it true or is it false? And that actually, and what it actually gives you is a 2 to the 3rd data points. You can see them organized here. And it's always very important when I try to give people advice. If you want to understand an experiment, do what many experimentalists do not do, which is set up this kind of ANOVA table. It's going to clarify your life. It's really going to help you. And it's important to do. So what do? You have 8 conditions. So you expect for there to be 8 data points. For a condition, the data point is like the mean of everything. And let's assume that we're not looking at the distribution around the mean, namely error bars. And what we end up getting, what we end up getting in this experiment is a huge difference between sentences which do not contain a negation. And we can see it as we look at the mean between the true and the false, which is what this red arrow denotes. It's a huge difference in all cases. And we get a very tiny difference between the antonyms. So you might have thought, what is above? It's not below. What is below? It's not above. It's quite superficial to think that, but some basic intuition would cover this kind of stuff. And what's really striking is the gigantic difference between the differences. Okay, so you can see, for instance, that this particular data point, namely the false sentence on the affirmative sentence with below, which is this which is this data point, and the true sentence on the sentence, or the one with negation here, each of them stands for something, and you can see that the biggest effect here is an effect of negation. It's gigantic. But, you know, there could be like a zillion explanations as to why that is. For one of them, there's an extra word, and the fact that you have some kind of a contraction here doesn't absolve you from anything. It's like a little bit too naive to think of. Okay, so keeping that in mind, we might move to something else. And this is, and again, coming from the same group, these guys, Justin Carpenter and Marcel Just, is extremely active until this very day. He's a big guy at Carnegie Mellon, and doing mind reading. And one condition they had in this, in an experiment they had degree quantifiers like many and few. It's like you have to fish it out 50 years later, but if you try to, sometimes it's successful. And what they did was they had sentences like those that you see here, and each of them had an image. It had 2 dots in one color, 14 in the other. These are not the original stimuli, but it's good, close enough to what they had, and you had to indicate if it's true or false. That was basically it. And if you look at the reaction times, they gave you an interesting pattern. So what it actually shows you is, first of all, you get the same kind of effect, namely this huge difference between sentences that are downward entailing and those that are not. That's one thing. But more interestingly, perhaps, you get an interaction with truth value. Previously, this did not show any, I mean, there was no apparent effect. But here, all of a sudden, there's an interaction with truth value. We'll get to that in a second. Here's what they said. They said, well, you know, when you think about it, it lends itself to some kind of a decompositional view. So what is few? Few is not many, or something like this. And if you want to be convinced that the negation has to decompose many, and it has to decompose few and not many, just look at the reaction times. They didn't quite say that, but this could have been said. But this is an empirical argument for, if you want to decompose something, then you want to decompose few. And you also get this kind of interaction that we will return to with truth value. Namely, the false affirmative takes longer than the true affirmative, but the pattern is reversed with the negatives, namely with the downward entailing ones. Well, for those of you who heard about Barwes and Cooper and witness sets, it should ring a bell, but I'll get back to it in a few minutes. Okay, so this was the beginning of it. And then the question is, why do you get the interaction? The claim here is there's some kind of a processing strategy, a verification strategy that says you should always go to the bigger set of dots. And then if you want to see if the bigger set of dots is the one over which that's the predicate, sometimes you have to shift to the other guy. That's the idea. It's not the best explanation on earth. It is an explanation. For one thing, you have 2 differences and you invoke 2 principles for them. So you might as well just recite your data. Okay, there's nothing much beyond that. But this is a little bit of something. They actually didn't even discuss it at the time in a serious way, because it's one condition buried among many, many conditions in a bigger experiment. So they did mention something, they did mention something, but not much. So here's the plan. You know, first of all, I'm going to look at monotonicity-related experiments with a single downward entailing operator, like what you see. We'll discuss it. I'll describe to you some relevant behavioral results, some relevant fMRI results. This is what we're basically going to do today. And what we're going to do next week, namely in my departmental seminar next week, is to go through all the rest. Namely, we're going to look at monotonicity-related experiments with more than one downward entailing operator. So we're going to look at flip-flop, basically something that's quite inspired by Vincent Omer's work on French. I'm going to show you experiments in Hebrew and give you a little appendix that, in fact, at least phenomenologically speaking, everything about flip-flop is replicated in that language. And then we're going to look at experiments that are both processing experiments and actually just hot off the, not even the press, but hot off the analysis experiments with two downward detailing operators in fMRI. It's really difficult to get effects there, but we actually managed to. This is mostly work by Ian Tan, my graduate student in Jerusalem, who's finishing her dissertation as we speak, basically. And then I would put a lot of emphasis on ruling out alternative interpretations, non-linguistic ones like learning and things of that type. I think it's important if we want to connect to a broader community. So this is what's going to happen. So without giving you a lot of background, I just want to say that we set up about 10 years ago, we launched a series of experiments, which I'm going to describe one. The main advantage, there were many motivations, but I'm generally very much in support of certain types of historical revisionism. So let me revise in most domains of history, especially in the domain of the history of science. So let me just say briefly that using pairs like more and less is a way to get around the problem of the extra word that negation gives you. That's one way of doing it. So if you want to say, no, it's not the morphology, no, it's not by counting words and things like that, okay, we bear the negation in some operator and we get that. There are other reasons, and I think the main reason is this guy sitting here. So to the I think Martin's work inspired a lot of this stuff, but I'm not going to start. I'm just giving him generic credit, which he greatly deserves, rather than pointing to every single point to which he contributed. Okay, so this experiment that was done by Isabelle Deschamps and Galit Agmon, but also Jonathan Levinstein, my closest, perhaps, collaborator in Jerusalem, who's a computational neuroscientist, participated as well. And the experiment was relatively simple, except the design ended up being complicated. So I'll begin by describing how each trial, what each trial looked like. And you basically heard a sentence like any of these two. The duration of it was fixed. Maybe the duration of the duration of the sentence, as you can see here, may not be fixed, but following a period of after 3 seconds or 3.4 seconds, actually, in this experiment, you started seeing an image. That was the setup. The image contained a bunch of points, and as you can see, they were scattered in a matrix way. There are all kinds of reasons for that, which I don't want to get into now. But basically, the idea was to block the subjects from being able to predict the numerosity here from the surface area, from summing up surface areas. That was the basic issue here. It was very much inspired, in addition to Martin's work, it was very much inspired by Manuela Piazza, who at the time was a graduate student at Stan Dehaan's lab near Paris. And the idea here was, since quantification is strongly related to quantity, let's see whether there is an interaction between any formally describable linguistic property and basic rules of perception, mostly Weber's law. So Weber's law, for those who have never heard about it, says that it's supposed to respond to the intuition that if I give you two weights, one is 1 pound, the other one is 2 pounds, and you're supposed to say whether they're the same or different, it's easy to do it. But if you give you two weights, one is 71 pounds, and the other one's 72, you're not going to be able to do it. So the idea is that in order for you to detect a difference between things, you don't calculate the difference, but rather the proportion. So the proportion between 1 and 2 is half, and the proportion between 71 and 72 is way closer to 1 than you would like. So it makes it more difficult. That's the basic intuition. So what we did, we had these two types of sentences, and we measured reaction times. And these two types of sentences, each was presented many times with any of these 7 proportions. And the question was, 1, will we get any kind of effect with respect to the, now we can tell the monotonicity of these, and 2, would it interact in any interesting way with a non-linguistic factor such as Weber's law? And we have ways of calculating, these are formally stated relations, so we have ways of calculating them reasonably accurately. But then we had like another thing. And the other thing is this. We wanted to see if there's anything having to do with, in a sense, the direction of the relationship that's being computed. You might have argued that we should have used comparative sentences. And the answer is you're absolutely right. We didn't think about it early on, but we came back to it later and we get exactly the same effects in comparatives. Again, it's a story on its own. I actually presented some of it about a dozen years ago here. It just shows you how old this work is, but I think it's still instructive. So we presented these kinds of quasi-algebraic expressions on the screen and basically asked people to say, you know, whether the instruction matches the scenario. We trained them in the lab before a little bit. We gave them all the possibilities. The idea is to have your subject as much with you as possible. And this way, you don't have to, you know, there's no uncertainty, nothing like that, and you can focus on the variable of choice. So people who tell you that you train your subjects, of course you train your subjects, but not on the variable of choice, okay? Which reminds me, sorry for being a little bit associative, but it reminds me of a very important anecdote statement that an old friend of mine named Edwin Williams, who used to be a linguist, but now is retired, once told me. He said, you know, people complain that we use linguists as subjects. They're wrong. I never use linguists for my experiments. I only use good linguists. And I think it's a very important, I really think it's a very important lesson. You know, if you don't know exactly what you do, and you just go and collect your data arbitrarily on the web or through Amazon Mechanical Turk, and they sit there and they're past their 6th beer, and you have no way of controlling. I've done that. Okay, and you have no way of really controlling and making sure that you can exclude those who are past their 2nd beer or something like that. Your experiment ends up being worthless. And it's really important to remember. I mean, sorry for pontificating to the converted or something like this, but it's like an important lesson to remember. And I think Edwin's statement was great. So we did that. And in fact, initially, we started off by presenting this whole bunch of things together. And then a guy named Martin Huckel told us, well, you know, maybe when you see this, you read it from left to right. And when you see this, you read it from right to left, which we hadn't thought about. And so we ended up redoing the experiments by having it unfold. So over this period of 2.8 seconds, first you saw one, then you saw this added to the picture, and then you saw this, and there's no way back. You don't have enough time. So we basically simulated, thanks to Martin, we simulated the unfolding in time, the unfolding of auditory sentences in time, and that's how we ended up. And here's what we got. Okay, so the experiment was really, really complicated with lots of things because we also played with different, not just with different proportions, but with different numerosities. But I'll spare you that. It's multifactorial big time. Here's what we got. For the linguistic material, what we got, and you can see a hint of it, is you can say a main effect of polarity, of quantified polarity. In a minute, we will see many more results, but you can basically see that, you know, for each proportion, each of these data points stands for a lot of trials. Many subjects, many trials. It's kind of a solid experiment. You can see error bars here. And for this corresponds to the mean reaction time on this image, collapsing across truth values. And this is what you see here. And you can see that as the proportion gets closer to 1, reaction times go up. And then as it gets further away from 1, the proportion between the two, the reaction times go back down again. You can see that, okay? And you can also kind of get a hint that these lines somehow run parallel to one another. So you can really see some curve that is fitted here. You can see it in this perforated line, and you can measure whether this parallels that. We'll get to that in a second. So there's nothing new here, okay? So we learn anything new? Kind of, yeah, we learned that, more and less behave like many and few, and with more subjects or something like this. That's all we've learned. But here's what we also learned. One, the effect is extremely robust, and in fact, you can replicate it with virtually every subject. So if you look here, each of these bars stands for the negative versus the positive, and you can see that for the most part, I think there's like 2 exceptions. One is here, one is somewhere else. You get kind of a reversed pattern. It's extremely robust, and we've done this as our basic condition 1,000 times since then. You don't miss it. Secondly, if you look at what you get in this condition, you get nothing. Really nothing. And in fact, this is what prompted Martin at the time to say, well, maybe they're reading it in the reverse order. And that was a serious consideration. We hadn't thought about it. Okay, you go back to the drawing board, you do it again. So this is result number 2. Again, many people and so on. Result number 3 is the summary statement of what you've seen. Collapsing across all subjects, everything together, you get an interaction effect. Namely, the difference between more and less and more is way greater than the lack of difference between greater than and less than. This is the interaction effect. We call it the net negation effect. And this to us is now going to be the hammer in which we're going to start looking for things to knock down. That's the thing. This is what we're after, namely the effect, the polarity effect minus whatever effect can be by there being something that remotely resembles it in non-linguistic notation. That's the idea, okay? Another thing which is really important are sanity checks, what they call a neuroscience sanity checks. Let's see if we can replicate standard stuff. And the standard stuff is Weber's law. So there is a way to check whether Weber's law is respected. It has to do with logarithmic compression of the x-axis and fitting curves and seeing whether some measure of approximation improves or not. I'm not going to go through the details of it, but basically we replicated Weber's law on this data set in everyone, like on every test that we subjected it to. I can give you details later if you. So this is one thing. A second question is, do these lines run parallel to one another? Do these curves run parallel to one another? So you could imagine all kinds of relations that would hold between that curve that describes subjects' behavior on more, given the different proportions, and subjects' behaviors on less, given the different proportions. Maybe they have a strategy that is bound by each. So maybe the curves would look like this. So, the sigmas of each of these curves would just not be the same. So there's ways of doing it. You use permutation tests. This is why I get somebody with computational neuroscience muscle, because I'm like a 0 in this kind of stuff. And the result is very clear. They're basically run parallel to one another, these two lines. Okay, so you can see if you want an argument for modularity. When you talk about quantifiers, which are expressions of quantity, you can see there's a direct argument for the modularity of the two systems. The polarity effect is totally unaffected by anything perceptual. People don't like these kinds of arguments because they're too complex. You want to argue an argument with modularity, give me A, compare it to B, and let's see that they're unrelated. This, you have to go through some steps and people get a little suspicious, but it is an argument for modularity. It also shows you that this business of focusing on the larger set, it wouldn't be the right strategy because it should be sensitive to relative set size, and it's not. This is, I'm talking about the Just and Carpenter. So this is the summary statement here is this thing, this net negation effect. And with that at hand, we went to the next step. But no, wait, I think I have a little chapter before that. I have a little chapter before that. Many people think, in the world of psycholinguistics, many people think that sentences with negation, the way they're processed is you strip them off from the negation, and they actually attach a specific cost of 3/4 of a second to it. You strip off the negation, and then you reprocess, you reparse the sentence. And Galit Agmon, an ex-graduate student of mine, who's now at the medical school at Penn, she tested that. And what she did was she kept increasing the distance between the sentence and the subsequent image. And the idea was, well, if you strip something off its negation in whether abstract or concrete way, then if I give you some more time, you know, you're gonna manage to beat the clock and there's gonna be no difference. And you can see here, as you increase the delay in image presentation, the difference persists. It gets a little smaller, it's true, but it persists and it's significant through and through. So this is a very robust effect, this polarity. It's extremely robust, and I highly recommend to anyone who wants to do an experiment to keep it in mind, because this is what you want to use as your basic setup for more subtle experiments than this. I mean, things which are linguistically more subtle. So this, of course, a time to stop for a second and say, wait a minute, where's truth value? You know, I collapsed everything I've presented thus far, collapsed everything across truth values. So what about truth value? So, you know, one thing that's funny is that, you know, when you read Barway's and Cooper's paper from over 40 years ago, you notice that they discuss witness sets, which is basically a sampling strategy. So, you know, how do you verify a sentence that's upward entailing? The claim is you look for a single example that makes it, for a single instance in your scenario that makes it true. How do you falsify it? Well, that's a different story. But the point was that the sampling strategy they proposed, which they call the witness set strategy, is one that distinguishes very clearly upward from downward entailing sentences. And what they did was they said, as you can see here, you know, verification of a proposition that contains an upward entailing function with less steps than one with a downward entailing. So the idea is, if it's downward entailing, you have to go through each instance to make sure that it doesn't violate the downward entailing. It's like, it's not, for each instance of which the sentence is said to be true, it's not more than that, it's not half or more, something like that. And they said, we predict that response latencies, you know, would actually be expressed by that. So here is a historical puzzle for somebody who likes history. Bowers and Cooper's paper it's from 1981. They had the evidence, namely the paper that I showed you from 1971 shows exactly something along these lines. It's, you know, that paper was around for 10 years. Now, mind you, neither Bowers nor Cooper read psycholinguistic papers, but the interesting thing is they were one building away from the building in which Herbert Clark was, and I'm sure that they talked, and I have no idea why they didn't use that reference to bolster their claim. But the thing is, whichever way you go, this claim is very, very unclear. And the reason it's unclear is because they don't take truth value into account. Because the same the same upward entailing sentence, once falsified, is flipped, and vice versa. So what you would actually expect is for the reaction times to show you this kind of relationship. You know, it's like the falsifying an upward entailing sentence, all else being equal, falsifying an upward entailing sentence should be as costly as verifying a downward entailing sentence. So where is that in the equation? It's not. Well, we kind of, again, following Martin's lead, we tried to look at that. I should have actually flipped it here and said something about, you know, that if you look at the sets that you see here, you know, you need one sample to verify, one instance to verify an upward entailing sentence, but you have to be exhaustive in falsifying the downward entailing one. And these would be the predictions. This is like some kind of a prediction. So what you would expect is, you know, if truth value does interact with reaction time, you should expect that this kind of relationship, namely a higher cost of falsification than a verification of an upward entailing one and lower cost of the downward entailing one. And if this account is not right, you should expect them maybe to look the same. These are expectations. And I'll just show you one thing that, so there are two interesting things here. First of all, if you go back to the 1971 result, you see that they did not quite get what you want, because what you want is what you want is this. Where is it? What you want is this. This is what the Barwise-Cooper plus would predict, but you don't get it. What you rather get is this, you know, you get a big difference. So the polarity effect overrides big time whatever predictions there would have been of the Barwise-Cooper thing. Second thing, which was pointed out a long time ago by Jonathan Levinstein, if indeed you use a sampling strategy, then it should be sensitive to the size of the set from which you sample, especially if it becomes exhaustive. And we see nothing of the kind. Nothing of the kind. So it's not at all clear that this witness set trick is the one to do the job. And you know, you can go back to Martin's work about the Barwise-Cooper approach, the general quantifiers, but you know, these are a distinct set of arguments. Okay, so yeah, here's why we never published it, this aspect of it. We got a beautiful picture, and it's beautiful because this one is kind of careful, if I can recommend my merchandise, okay? Because it doesn't just look for an interaction effect between truth value and monotonicity, but it also looks for an interaction between this and the control case. Like if you do it seriously, you better do it seriously and show that in fact the interaction is a three-way interaction. It's like modulo where you would never expect, which you should break down by truth value as well. And we got it, but the problem is this is the only instance in which we got it. We got a mess elsewhere. You know, maybe you'd be interested in it, in looking at the distinctions between the quantifiers, but we never did anything with it. So just so you know, it's not a great success. Okay, next chapter, the last one for today, is the functional MRI. Because yesterday, you know, I wasted an hour of your time on anatomy. I might as well make some good use of it. And here's the good news. The same team pretty much, except now we had the anatomical muscle of Katrin Namutz, the legend from yesterday, okay? And we did basically the same experiment in the magnet. It was a little smaller because in the original behavioral experiment, we had subjects come back to the lab 4 times. These were very well-behaved McGill students. They're good guys, and they're patient enough to wait for 4 sessions until they get their $50. Okay, and still there was quite an attrition, you know, I was expecting a demonstration. If had I done it in Israel or something, I would get a demonstration, you know, under the building in about 5 minutes, but in Canada, it doesn't work this way. So they came back 4 times into the lab. You can't take a subject and bring them 4 times into the magnet, at least not me, not with my limited resources. So we had each subject sit in the magnet for the short duration of 90 minutes. It's very difficult. It's really difficult. Okay, and it's not just difficult, it introduces noise because they start moving. Okay, so it's a little tricky, but we managed to do it. And the basic idea that we had in mind was, again, you know, we did exactly the same thing. Here is some very simplistic model by which what you do is you have some kind of linguistic analysis, you end up with some representation, you have some kind of a scenario analysis, and then you're supposed to make some decision. I can't think about anything more primitive than that, but at least it gives you some vague notion of the time course of this and what you should expect. And the idea was to use this rough thing in order to divide up the trial into 2 different phases, because previously we only measured at endpoints. So, you know, we wait until the subject does whatever they do, and we measure the distance between some fixed point, the time it takes them between some fixed point and the point they pressed. But we have 1 measure per sentence. Here, we actually keep scanning them along the sentence, and we have more than 1 measure. So what we did was we actually divided up the duration of this into 2 phases. Essentially, phase 1 was the part which was auditory, and phase 2, or this aspect of visual, and phase 2 was this, and we analyzed them separately. And it actually ended up being interesting. So here's what we got. We had 21 subjects, whatever, and we knew what we were looking for. We were looking for this net negation effect. This was the thing. So we asked our analysis the following question. Give me those brain areas that are big enough to count as a cluster, as an activation cluster, in which you get a significant net negation effect. We wanted to get the same picture that we had previously obtained in the behavioral experiment. We wanted to get the same picture replicated, but here the dependent measure is no longer time, but rather relative signal intensity. And the answer was, yes, there are such areas. In fact, there's 2 such areas we will see in a second. There are such areas which show you exactly the same pattern. I hope that you see the similarity between the 2 bar graphs. And these are similar enough statistically, and they live in 1 area, which is this. It's the anterior part of the left insula. Remember, we talked about there being what some people call the 5th lobe. So it's like something that would be a little bit like a brain lobe, but it's hidden behind. It's kind of concealed and seems to be isolated on certain splicing modes, and that's why it's called insula. Okay, so the left front of the anterior part of the left insula is the one that's activated. And in order to be more convinced that it's not just accidental, because as I showed yesterday, it excludes, and you'll see it again in just a second, it excludes the typical language areas, namely Broca's area. It's adjacent to, but excludes. And we can calculate it, given that we have the anatomical maps, we can actually calculate and show that it excludes them. When I get such things, I don't start yelling, I made a discovery. No, it's probably some artifact, you know? So you want to be convinced that it's not an artifact. And so we added 2 analyses that would convince us of that. Analysis number 1 is we wanted to see if there is a systematic relationship at the individual level. This is Galit Agmon's great contribution to this. If there's a systematic relationship between the signal intensity that individuals give you on this net negation effect and the reaction time net negation effect. So you could imagine that the world is divided into fast and slow negators. If you're a fast negator, your differences are small. If you're a slow negator, you pay a big price for negation. And the question is, do these things reflect on the two different measures here? And the answer is yes. So you plot this, each of these points is a single subject, and whatever value we derived for them, for the intensity in the time domain, and whatever it is that we derived for them in the signal intensity domain. And then we just, we plotted it. And the correlation is significant. It's like 0.4 something, and it's significant. This is like an important tool. So this is step number one. Step number two, which is more important, is to see if the area that we spotted here by this cluster constitutes an anatomically coherent area. I chewed your ears yesterday about anatomical coherence and about small regions that are cytoarchitectonically characterized. So, we sent off our anatomists to map that area. It had not been mapped before. So, Francesca Yanili and Katrin Amunds and others mapped it on both hemispheres. The interesting thing that you see, if you remember the images from yesterday, is that here the picture is much more elegant. Namely, if you look at, so this is some kind of a heat map, and the heat map looks like they're concentric kind of circles, ellipses or something like this. In the language areas, it doesn't look as elegant. It's kind of shifted and full of edges and things like that. Maybe there are reasons for that. But the important thing is, this is a coherent area, and this guy sits right down the middle of it. So we have what would appear to be some kind of an anatomical module of something. And the question is what that something is, but let's hold it. Because I want to show you, and I think I still have like 2 or 3 minutes, how difficult this is. I'm giving you a punchline, but there's a lot on the way to be convinced. Thing number one, you want to get some kind of a sanity check, not just from the language aspect of it, but also from the image, from the numerosity aspect of it. I mean, this is also a numerosity experiment because we present people with proportions. If we try to replicate the standard methods that are used by Stan Dehan, Manuela Piazza, Veronique Izar, this whole group of fantastic students of the numerosity world, we do replicate the results in that we obtain activations exactly where they belong, namely on the two sides of the intraparietal sulcus and the parietal lobes, bilaterally in both hemispheres. So this is sanity check number one. But here is not sanity check, but problem number one. And the problem is that the net negation effect that we obtained, and only for phase one, I showed you results only for phase one, namely the part in which they're listening to the sentence, also spotted something that's roughly Wernicke's area. So why did I tell you stories about there being a unique region? Well, the reason is when you study it more carefully, you realize that the properties that you require of your area, namely a correlation between the behavior at the individual level, when you plot all the individuals, the correlation between the behavior and the signal intensity, you find nothing of the kind in the other one. And you actually don't find anything of that in phase two. Nothing happens in phase two, whereas the two phases, the auditory phases, the image phases in this region and the insular region persist across both phases. So this seems to be a really good way for me to know where I want to focus on. Remember, this is the brain, a lot of noise. So this is where we're focusing on. I just want to show you, just because we have a good movie, I want to show you the same thing relative to the typical language areas, which is what you see in yellow and in orange or whatever color this is. And I want you to see, I'll switch it. Yeah, oh, come on, I'm so bad at it. Okay, so here's what you see here. What you see here is the language area. You see the anatomical cluster, and you see the functional cluster where I put the question mark, because we don't know what it is yet. So this is the functional cluster, and this is the anatomical cluster. Don't be impressed by the fact that one is bigger than the other, because it's a matter of thresholding, how you threshold, your measures. So it's really nothing much. What's important is you can't really see it here, but the centers of mass of both clusters are almost bingo, almost exactly on the same spot. I'm going to stop in 1 minute, but what I want to show you, so we have convergence. Convergence in the sense that we do find something, and we have a new puzzle, which is what is the nature of this area? At least we know it's not in the standard areas, which some people like me have claimed that it has to do with syntactic movement and things of that type. So at least it's not as if any language effect falls within the same garbage area called Broca's area. And the important lesson here, I think, is mostly methodological. It's not so much about results, but more about how you get them. And that's the idea. But before that, I want to show you, and I don't know, maybe I should move to the next one. It's because you can hear it. I'm going to skip it, forget it. But we did the same thing with aphasic patients, because I think I forgot to click on the sound box, and it would take me forever. So maybe we can just skip it. We did the same kind of thing with aphasic patients. We did it in Argentina a long time ago, and you have the results, and they look terrible. Okay, and they look terrible. It's just 6 patients. This is the quantificational stuff. It's with muchas, muchos, and muchos and pocos, and menos de la mitad, and más de la mitad, so more than half, less than half, many and few. And you can see this is like each individual patient's, their score from 0 to 1. You can see there's quite a lot of variability between the patients, but at least the one little piece of good news here is that at least when you look at how they performed on the inequalities, with the exception of one who I think ironically had been a math teacher before she had a stroke, and almost everybody was quite good. That's the only good news. I'm showing this to you just to tell you how difficult this is and how much garbage data you get along the way until you find the gem. And I think with this, we're going to stop. And once again, the continuation, which is the other half of this, namely how you do something that's really linguistically worthwhile, hopefully I'll do in a week in the departmental seminar. And tomorrow I'm going to talk more about syntax.